Hello folks, and welcome to the channel, or welcome back. And this is part number 2 of the CAN bus, and in this episode we're going to look at the electrical specifications of the CAN bus. I'm going to give you some slides and some explanations, and then we'll be using a breadboard to actually simulate the CAN bus with real CAN bus transceivers. We also know that the CAN bus controllers are connected with twisted pairs. We call that the CAN bus. And we also know that the CAN bus is actually terminated with a 120 ohms resistor at either ends. If you want to know how all that is done, then please check the previous video. But now we need to have the controllers to communicate with each other, and they need to communicate over this physical wire, the twisted pair. And that's not all that obvious, because controllers, they are sending out digital messages in the form of ones and zeros. And those are not all that suitable to travel across longer distances and at a high frequency over the CAN bus. So I'm going to take you through a couple of slides now, trying to explain on what it all is, and then we'll be using a signal generator, we will be using the scope and the breadboard here to actually demonstrate to you what I'm explaining in the slides. So here we have the breadboard, we have one transceiver on one side, we have another transceiver on the other side, and we're going to connect those up with our twisted pair cable, which is actually our CAN bus, with the terminating resistors both on the left and on the right. For testing the electrical signals, we will be using an oscilloscope. A voltmeter, well, like this one, might work, but it's not all that easy to demonstrate. And we'll use the different traces on the oscilloscope to show all the different signals. And I'll use a signal generator to set up some of the signaling, pretending it's a controller, and we will be using a square wave for that purpose. And we'll select the square wave, and we will work it at 500 kilohertz. And the amplitude that we're going to use is about 5 volts. Look over here, and we have 0 volts offset, and our duty cycle is 50%. So let's start with the slides, if you don't mind. In the following slides, I'm going to take you through some explanations on the transceivers used on the CAN bus. And then in between, I will show you some practical proof of what I'm saying. So with any further ado, let's start. So we already know that we have in a car multiple CAN controllers. That could be your ECU, it could be your ESP, it could be your ABS, it could be any of those controllers, and they all need to communicate with each other. So controllers, which we call CAN controllers, are going to exchange digital messages between them to communicate. And of course they can't do this directly between them because they have to get over the CAN bus. And now the question is, how do they get over the CAN bus? Keep in mind that controllers, when they are exchanging messages, are using just digital patterns, right? The ones and zeros in a certain sequence, forming a certain message. So the messages being transmitted by one controller to the second controller are basically ones and zeros being represented by 0 volts for a 0 and 5 volts for a 1 bit. And the sequence of those bits is forming the actual message. The receiving controller, of course, wants to receive those bits in exactly the same sequence. And if not, then we have an error condition. So all this sounds pretty logical, that we can transfer messages between CAN controllers as a string of serial ones and zeros between the transmitter and the receiver. And of course, controller 2 can also talk to controller 1. It works in both directions, but not at the same time. But we have a problem. Transmitting zeros and ones in the form of 0 and 5 volts across a wire is not really a good way to communicate, because those signals are going to get distorted very quickly. Keep in mind that the wire has a capacitance, an inductance, and a resistance, and that is going to cause deformation of that DC signal. And it's going to make it extremely hard for the CAN controller who is on the receiving side actually to read the bits. In fact, it may not read it at all, and we are going to have errors. This is something we don't want. Now, if the wire is short, that might work, but not on longer wires. In a car, well, it is very prone to all kind of interferences as well, and the cabling can be pretty long. So we got to do something about this. This is a fairly long cable, and I'm going to try to demonstrate to you what this cable would do to your digital signal of ones and zeros that are toggling between 0 and 5 volts. I have connected my signal generator on one side and my scope to the other side so we can actually have a look on the trace itself. So this is the signal we see on the scope. The input is a nice and clean square wave, but what we see on the cable is overshoot in different directions. So this signal is getting really distorted. If I change the frequency, you will see that this is going to get quite a bit worse. So the higher the frequency, the worse the signal becomes. And at some point, we almost get like a sine wave. And that's going to become very difficult for the transceiver, which is receiving the signal, to actually decode it. The way we overcome this problem is by using a transceiver. And a transceiver is a chip that is going to convert digital signals represented as zeros and ones that are typically toggled between 0 and 5 volts into a balanced signal. And the balanced signal is going to toggle on the CAN high between 2.5 volts and 3.5 volts, and for the CAN low it's going to toggle between the 2.5 volts and the 1.5 volts. And what is important here to notice, it is the difference between CAN high and CAN low that is going to be important for the receiving part of a transceiver. Let me give you a little walkthrough on how CAN controller number 1 is sending the message 01010010 towards CAN controller number 2. The CAN controller 1 will forward the bit stream in sequence towards the transmit part of the transceiver. The transmit part of the transceiver will convert the bits one by one to a balanced signal, as you can see on the bottom of the screen, and then the far end transceiver will detect the signal and convert that balanced signal back to a digital signal and forwards it to the CAN controller number 2. What is important to note here is that a 0 applied to the transceiver of CAN controller number 1 on the transmit part results in 3.5 volts on the CAN high and 1.5 volts on the CAN low. It is also important to note that a 1 applied by the CAN controller number 1 to the transmit part of the transceiver is going to result on the CAN bus, CAN high to toggle to 2.5 volt and CAN low to toggle 2.5 volt. And it's exactly that difference in voltage that will allow the receiving part of any transceiver on the bus to make the difference between a 0 and a 1. Balanced signals transmitted by a transceiver are always seen immediately by the same transceiver on its own receive. That is an internal circuitry on those transceivers. Also note that all transceivers are all connected at the same time in parallel to the same CAN bus. So in other words, if one is transmitting, then everybody else can receive. And that is why you will hear quite often the term CSMA-CD, carrier sense multi-access with collision detection. Very similar to what you see on a local area network. With this in mind, we can create a little truth table. If the binary state is 0, then we will have 0 volts or near to 0 volts on the digital side of the CAN controller on its TX or RX. But the CAN high will be toggled to 3.5 volts and the CAN low to 1.5 volts. So we are having a difference of 2 volts. The CAN logic, we call that a dominant state. So a binary 0 is a dominant state on the CAN bus. This is going to become very important once we start talking about the priority scheme and the arbitration on the bus. A binary 1 on the CAN controller
TX or RX is typically 5 volts or near to 5 volts, and the CAN high is 2.5 and the CAN low is 2.5. In other words, we have no CAN differential, the differential is 0, and we call this on the CAN logic a recessive state. So now it's time to put the theory into practice, and this is the CAN transceiver, the MCP2551, that I have on the breadboard, and you'll see it very soon in real life. And it has a couple of pins. We have the 5 volts power supply, we have the ground, then we have the data from the CAN controller and the data to the CAN controller, and then finally we have the CAN high and the CAN low. So there's not a lot on this, and typically this chip is implemented inside your CAN controller, as I mentioned before. So now let's have a look on how we're going to connect this all up on the breadboard. This is how I'm going to cable up the transceivers. Basically, we have CAN high and CAN low connected between the two. There is a resistor between CAN high and CAN low on both sides of the transceiver. I don't show it in this picture because I forgot to draw it, but I guess that's okay. You will see it on the real breadboard. Then we have the power supply feeding 5 volts to both boards and the ground. And then we have 2 more pins, data from the CAN controller 1 and data to the CAN controller number 1. And then on the other side, we have the data to CAN controller 2 and data from CAN controller 2. Nothing very complicated here, but this is going to be the mockup we're going to be using.
So let's start by hooking up the plus 5 volts, the power supply. We'll also hook up the ground, because that board needs to be provided with power. And by the way, these are the same transceivers that you would find on the real CAN bus. I'm also going to create the CAN high, which is yellow, and the CAN low, which will be green. And then I like to use, for the transmit data, so the data coming from the controller, a white cable, because that's the one we're going to use to connect the scope to and the input signal. Let me continue wiring up the mockup here with all the wires, and then we can do the actual testing. I'll be right back with you.
This will be our first test, which is a CAN transceiver throughput test, and see if what I told you is actually true. I'm going to connect a signal generator generating a 5 volt square wave at 500 kilohertz to transceiver number 1. And I'm going to connect it to the pin called CTX. So this is the input signal towards the transceiver, normally coming from your CAN controller. I will connect an oscilloscope with trace 1 to the same transceiver 1 to the CRX. This is typically the receive side, or the part which is communicating back to the microcontroller. Now, as I said before, the internal circuitry of these CAN bus drivers, they immediately loop back the transmit signal to the receive signal. So we should see exactly the same signal. Now, at the same time, transceiver number 1 will transmit over the CAN bus towards transceiver number 2 that same signal. And at transceiver number 2, we'll hook up the scope with trace number 2 on the CRX. So basically the signal that would be going to the microcontroller. So we should see equal signals on all sides. So let's give that a try. I could reverse this whole thing as well, but I'm not going to do this because it's the same in the other direction. As people say, the proof is in eating the pudding. So let's get to the breadboard and see if I was right or wrong.
So this is our test scenario number 1, where we are having the CAN bus wiring, the terminating resistors on it. And I have my transceiver 1 and transceiver 2. It's all cabled up. And I'm feeding on transceiver number 1. I'm putting in my signal from my signal generator. And this is my input signal. And you can actually see we're sending now 1 megahertz and we are running at 5 volts peak to peak, which would be the digital signal that normally your CAN controller would pass along to the transceiver. And I'm checking it with the red probe to see what the square wave is of the input signal. The second pin that I have here is the local direct receive back on that transceiver, as we talked before, and I'll show you that in a few minutes as well. And on the far end side, I have the gray probe right here, and this one is the receiving side. So I'm sending a square wave in, and it should come out on the other side, and it should be more or less the same. So let's have a look on the scope and see what we have. So on the scope, the red trace is my input signal, and you can see that's a nice square waveform. And the blue trace is what we receive on the far hand side. So basically the signal traversed the CAN bus, and you can see we have a little deformation. There's a little bit of ripple on it, but that's okay. So my input frequency now increases, and you can see the output on the other side just follows along. I also mentioned that the transmit signal on the transceiver is immediately fed back to its receive circuitry, and that's this pin I cabled up. So let's have a look if that is the case. And let's have a look on the scope. And there it is. So you can see that the transmit signal on a transceiver is immediately coupled back to its receive circuitry, as I explained on the slides.
Our next test is the CAN transceiver CAN high and CAN low signaling. So again, I'm going to use the same signal generation, 0 to 5 volts, a square wave at 500 kilohertz on transceiver number 1 connected to the CTX pin, so that's the input to the transceiver. And I will keep my oscilloscope trace 1 actually on the CRX pin, which is the receive side of the transceiver, and we should see there a square wave. I also will have my oscilloscope trace number 2 on the CAN bus. One probe connected to CAN low and the other side of the probe to the CAN high, and we should be seeing the signal as shown on the right hand top. So whenever the input signal on the transceiver number 1 is going to be 0, I expect to see on the CAN bus a 3.5 volt and a 1.5 volt transition. If the input is a 1 on transceiver number 1, then I expect on the CAN bus to see 2.5 volts for both CAN high and CAN low. So let's see if this is going to work.
The next test is to look on the CAN bus. So I'm going to move one probe to the CAN bus. I'm still injecting my signal as before, but now we'll clip on the CAN bus. And now with the probes connected on the CAN bus, I can see my balanced signal on the oscilloscope. So this is my signal. Maybe now we should check the signals and see if the voltages that I mentioned to you are actually correct. So I'm going to hold the display. I will use my cursors, and I'm going to first of all go to cursor A, which is for channel A, and channel A is the red line. And you can see that I have 3.62 volts because that's my CAN high, and we are sending a 0, so that should be high. And my CAN low is 1.5 volts, right there, 1.5. So that is about 2 volts difference. That is my 0. Let's move the cursor over a bit. Now I have for my B channel, or my CAN low, 2.62 volts, and my CAN high, I have 2.5 volts. So basically the difference between the two is almost 0 volts. And that is a 1 bit being transmitted. I think that we have proven the case that what I explained to you on the slides is actually accurate. What you have seen so far is the electrical behavior of the transceivers on a CAN bus. So now you know what kind of voltages to expect. Now the problem you will have on a CAN bus, if you're trying to read it with a voltmeter, it's not going to give you the right reading because these signals are switching way too fast. Now when the CAN bus is in an idle state, it's going to show about 2.5 volts both on CAN high and CAN low. But you never know, that can change any moment in time. So it's very hard to check this out. So therefore, really, you should invest in an oscilloscope so you can actually see the traces. Now, I'm not making any commercial for this brand, so let's take it out as soon as we can. And this is a very cheap oscilloscope, which is usable for CAN bus quick analysis. That's it. You know, this is pretty simple, very straightforward. Let me see if I can turn it on. There we go. And it has only one connector, which is a bit the sad thing, but you will see the waves on this one, just like you see on the big scope. and that's handy. So maybe I should hook it up so I can show you what it does. I'm just checking on one of the wires, CAN high I believe this is, and you can see it shows the trace pretty nice. Of course you cannot measure between the two CAN high and CAN low, but you can measure one at a time, and then you can already make a decision if the CAN bus is in a short or not. So the question now is, can you really troubleshoot the electrical levels with a voltmeter? You can try to use a voltmeter, but remember the CAN bus is having a lot of signals that are changing very quickly. It's a very busy bus. And also we have alterations between zeros and ones. So in other words, CAN high will toggle between 2.5 volts and 3.5, and CAN low will toggle between 2.5 volts and 1.5 volts. So you always have a variance ongoing. And that makes it very difficult to use a voltmeter to use that. But you can still try. If you measure CAN low towards ground and you measure CAN high towards ground, you should always have something around 2.5 volts and a bit more for CAN high, and you should have most likely something between 1 volt and 2.5 volts for the CAN low, and I'll show you that in a minute. Of course, that is not the best solution. The better solution is to use an oscilloscope, and it doesn't have to be an expensive oscilloscope. So I've set up the voltmeters to a DC scale, and I'm going to measure the CAN high first. And we have some traffic on the CAN bus. And let's see what it gives us. And I think what we measure is about 3.1 volts, and that's about right because the signal is toggling between 2.5 and 3.5. And then the CAN low is about 2 volts, and this is going to toggle between 2.5 and 1.5. So all depending on the pattern of the bits on the line, you may see different values. Right now we're looking at CAN high, and the signal on the bus is equal amount of ones and zeros. So if I'm changing that and I'm going to send far more zeros, that voltage should actually go up. So let's see if this is going to work. And now we're sending more zeros, and you can actually see the voltage is building up. If I'm sending more ones on the bus, the voltage should be going lower, as you can see. So that is a quick test, but then again, I'm controlling the data on the CAN bus right now, and on a live system, that's not going to be the case. You can do exactly the same thing on the CAN low, and you would see the opposite effect. Right now, I'm looking at the CAN high, and I'm applying a steady 1 signal towards the transceiver, and you can see the bus toggles to 2.4 volts. If I move my probe to the CAN low, it should be about the same. And as you can see, it's 2.4, so there's almost no difference. So folks, we've come to the end of this video, and by now you know how the electrical signals look like on the CAN bus. In the next video, we're going to look at the CAN bus protocol and trying to dig in a bit deeper into all the bits that you can capture on the CAN bus. Thank you for viewing, and I'll see you in my next video. Bye bye.